in this lecture we continue to talk more about flash A to D converters, because in the previous lecture we have discussed about 8 bit flash A to D converter, and we had shown that for 8 bit flash ADC, 8 bit flash ADC, we need 256 comparators, 256 comparators required, and then similarly you need 256 divider resistors. So, these two are very tough to achieve, because if we can have 256 comparators and 250 divider resistors, it is somewhat manageable, but then if we want to go for 16 bit flash ADC converter, 16 bit flash ADC, if we look for this, then I need 64,000 2 power 16 comparators, and then similarly 2 power 16 divider resistors. This is not easy to achieve. So, because 64,000 comparators and then 64,000 resistors, and then combining the 64,000 bits into 16 bit usable A to D output is not an easy job. So, normally 16 bit flash ADCs are normally not made this way. So, for this only subranging ADC is used. So, subranging ADC is used for 12 bit or 16 bit flash ADCs. So, let us see what is a subranging flash A to D converter. Subranging flash ADC converter, what is done is that you use only you have your input voltages to be digitized, V input, that is actually given to A to D converter, which is a 8 bit flash. So, you have a 8 bit flash here, basically it goes to your resistor divider here, so on, and then your comparators. So, basically it is a 8 bit flash ADC. This gives you output which is 8 bits actually. So, you have a 8 bit output here. So, you have a MSB here and then LSB here. So, this actually given to again 8 bit DAC DTA converter, which actually gives you output voltage corresponding to 8 bit. So, what you have done is you have actually put a A to D here, then you have put a DTA, then again you got back the analog voltage, but then this is only 8 bit output, but this DAC, even though it is a 8 bit converter, but 16 bit accuracy is maintained. 16 bit accuracy is maintained, in the sense that if I have a 8 bit for example, if it is a 8 bit DAC, 8 bit DAC, then 8 bit accuracy, if I look 8 bit DAC, 8 bit accuracy, then the error in this, for example, if it is 1 LSB, error can be error will be 1 LSB maximum. Whereas, if I look at 8 bit DAC, 8 bit DAC, 8 bit DAC, then if it is 16 bit accuracy, it is 16 bit accuracy, this will have a error which will be 1 LSB of 16 bit, this 1 LSB of 8 bit. In the sense, for example, if it is a for example, if I take 1 volt as my reference, for 1 volt reference, 8 bit DAC, 8 bit accuracy, the expected error is 1 by 256, that is roughly equal to 4 millivolt. For same 1 volt, for same 1 volt reference 8 bit DAC, 16 bit accuracy, error will be 1 in 2 power 16, that is 1 in 64,000, that will be roughly 16 microvolt. So, that is the meaning of 8 bit DAC with 16 bit accuracy. So, we have a DAC here which is more accurate than the normal 8 bit DAC, that is 8 bit DAC, but it is accurate to 16 bit. Now, what we can do is this analog output which is very accurate can be now subtracted from the input, and then we can make another 8 bit converter. So, I will show you the figure in the following page. So, what you do is that you have the input voltage V input. So, essentially you give it to, I have a V reference here and then I give it to input. So, this is 8 bit flash, then this is actually gives you output to 8 bit DAC, but 16 bit accuracy. This gives me the this as a V reference, and then this gives me output. This output, what I do is I will give it to a subtractor amplifier here. This I give it to a subtractor amplifier here. The difference between the input and this is appearing here, and this what I do, I will actually now amplify this voltage. So, I can amplify the difference voltage. So, we can get into the next page. So, we will have the amplified voltage coming here. Here we amplify this, say for example, for another 8 bit converter I need, amplify by 256 times, gains equal to 256. Then whatever the output is coming, this I give it to 8 bit flash, and this 8 bit will act as a lower 8 bits of 15 bit, lower 8 bits of 16 bit converter. This will act as higher 8 bits of 15 bit converter, higher 8 bits. This actually higher 8 bits of 16 bit converter. So, you have the lower 8 bits here and then higher by 8 bits here. So, you have the 16 bit conversion, but then we have used only here 256 resistors and the 256 comparators, and then here again used 256 comparators and 256 resistors. So, it is only totally 512 comparators and 512 resistors, not 64,000 resistors and comparators. Now, how this is working? For example, if we take an example, if I give for example 1 volt as input, and if my reference all taken as 1 volt, even for this also I take it as 1 volt. Then if you analyze the circuit, that if we have 1 volt, then the 8 bit converter would have converted this and then given all of them equal to 111 and 111, and of course, this also has to be 16 bit accuracy. 16 bit accuracy is required. Then this will given all of them 111, but then the final output, when this is converted, this is not going to be 1 volt, this will be actually 1 volt divided by 2 power 8, that is 1 LSP. So, 1 LSP error would have been left and you would have got 4 millivolt output from here you would have got 1 volt divided by 2 power 8 is 1 LSP, and the total you have a 255 LSP is there. So, if we take this, and the difference will come here as a 4 millivolt, because 1 volt and even all bits are high, that you are not going to get 1 volt, that will be 1 in 2 power 8 into 255, that will give you error of 4 millivolt. This 4 millivolt is actually amplified by 256 and that actually will give you 1 volt. Now, this 1 volt will be digitized by this converter, and then you will all get 1 1 1 1, all 8 bits will be 1. So, essentially you given input V input as 1 volt, and then the digital output coming as all the lower ones are 8 and the upper ones also coming as 8 bits, all high. So, that way with less number of comparators and resistors, one can get the required 16 bit converter. Of course, the conversion to be done in 2 stages, and the amplifier to be made. For example, if I want 16 bit accuracy, then I can have a gain of 16 here. But 12 bit accuracy, suppose if I want 12 bit accuracy, then I can have a gain of 16 here, and then I can put a 4 bit converter here, again that 4 bit will give me 111. So, this is actually called subranging A to D converter, which is very common in the flash ADC, because there is no way one can get 64,000 comparators and 64,000 resistors and make them a workable unit is practically not viable. So, almost all higher bit converters, flash converters are all actually subranging A to D converters. So, sometimes it is called it is also called as pipelined ADC. This A to D converters are very fast, because you have only the direct comparison with the comparator. So, the conversion time goes in nanoseconds. So, the advantage is very short conversion time, the flash ADC short conversion time, but it is costly. Then other advantage that we will see in the converter is that we have the inputs are compared with so many comparators, because the other major disadvantage is that we have, for example, the input voltage is divided by so many resistors, and then we are also putting so many comparators and comparing with the reference. So, we have this, we have a reference, we have V input here, and then we give this one to the second one, and then we have a V reference here, V reference here. So, we have so many comparators and so many reference voltages. This is again given to V reference. So, you will have, if you look at the output, so you have plus minus, so you have plus minus, and then the input will be minus and plus. Now, we have the output voltages, this VR. Now, if the input voltage, for example, if we take the comparators, for example, if I have 1 volt reference, and if this is 4 millivolt, and this is 8 millivolt and so on. So, if you see almost all comparators are all in the saturation stage only. So, because half the comparator, suppose if the input voltage is 0.5 volt, half the comparators will be high and other half will be low. So, all the time the comparators are all in the saturation level only. So, always all the comparators are in saturation mode only. That means, the input impedance seen by the comparator is not known, because our assumption that the input impedance is very high for the op amp is valid only if it is in the linear range, because if you take any comparator, we have plus minus and then we are comparing two voltages. Then if it is in the linear region, the bias current is what is taken at the input, but if it is in the saturated region, this bias current is higher. So, in saturation mode, the input bias current is higher. So, essentially what happens when the input voltage changes, the current taken by the each comparator changes. So, that actually is a problem, because we have to make sure that this current is very small. The current actually taken by the op amp is very small. This is to be ensured. So, this is one of the major problem, because when the input changes, the current taken by the comparator changes. So, it is essential that we drive the flash ADC with very low output resistance. So, it is essential that to drive the flash ADC with very low output impedance source, output resistance source. Otherwise, the varying current, that is the input impedance offered by the flash ADC continuously varies with respect to input voltage itself. So, it is essential that we drive this kind of flash ADC with very low output resistance. That means, if I have a flash ADC, then the input I give this one, and it is essential that we have a voltage follower at the input. So, the output impedance present by this is very low. So, always drive the flash ADC, with low output resistance. This is one of the major issue, and most of the converters now have inbuilt voltage follower, so that this problem is taken care. So, this is flash ADC, and the flash ADC you have even today, even nanosecond converters, 100 nanosecond conversion time, even 50 nanosecond conversion time flash ADCs are available. Of course, compared to dual slope and successive approximation ADCs, they are much costlier. So, if you look at these ATD converters, that we had seen 3 ATD converters so far, that is, one is dual slope ATD converter, ADC, and the second one is successive approximation ADC, and then third one is flash ADC converter. Now, this is used mainly for displays actually, where the conversion is very slow. So, you have 8 to 10 conversions per second is possible, that is all. 8 to you have 8 to 10 conversions per second, that is all possible. This actually have 1 microsecond level of conversion time. The successive approximation A to D is much faster, it is about 1 microsecond conversion time, and the flash ADC it will be about 50 nanosecond to 100 nanosecond conversion time is possible. Now, in all these things, if you see that we have issues, because after all this ATD converters, if you see, they all have a voltage dividers, or comparing the voltage and so on, the final conversion is achieved. They all have errors. So, if you look at them, that errors involved in all these ATD converters, that basically you have a problem due to, for example, if I have a ATD, we have a reference voltage and then we have a input voltage and then digitized output, digital output is coming here. And then the one thing is that resolution. The resolution is actually resolution of these ATD converters. Resolution is actually 1 in 2 power n. So, for example, 2 for 8 bit converters, it is for 8 bit it is 1 in 256. So, resolution actually you will get depending upon the number of bits. If 8 bit means you have 1 in 256, if it is 16 bit, it will be 1 in 64,000 is the resolution. But it does not mean that you will get the accuracy also that much. One main problem with the ATD converter error is that you have a reference voltage drift. We are using a reference voltage and the reference voltage is the main input based on which only all conversions are done. So, if we take reference voltage, so that drift creates a error in the output. So, the errors will be, one is reference voltage drift, this directly affects the output. Then the second one is offset voltage drift. Because if you have offset voltage, the 0 input 0 output is not the case in most of the converters. For example, if you take the converter for 0 volt, for 0 V in is equal to 0, V output need not be 0. This is actually a offset voltage, but this offset voltage changes with the temperature. So, this is another major error, one have to worry about this. Then the third error is gain drift. The gain of the ADC also changes with the temperature. So, these are all actually temperature related errors, That is when temperature changes, this reference voltage drifts and that produces error in the output, offset voltage drifts and then the gain also drifts and they produce a temperature related error. Now, without temperature related without the temperature related error, if you look at what is the inherent ATD DTA converter errors, they are all actually like this. So, the static errors, there is no not related to temperature. Not related to that errors are one, you have actually gain error, offset error, offset voltage error, then linearity error, then you have a differential linearity error. These errors are there always, is nothing to do with the temperature. So, even if there is no at any given temperature you have these errors and these errors actually of course change with the temperature. Of course, we are not much worried about differential linearity error changing or the linearity error changing with temperature. These two errors actually gain error and offset voltage error changing with temperature is a issue. So, what are these errors and why one have to worry about this? Now, if you look at the gain error, the gain error looks like this. For example, if I have a converter, ideal converter. So, we take to explain this 8 bit converter and then explain the these errors. So, take for example, okay, instead of 8 bit converter I will take 3 bit converters. So, example with 3 bit converters. Now, for example, if I take a 3 bit converter, so if I have a 3 bit converter which will have 1 1 1 as a digital output, So, if I have start from 0 0, then the next code would be 0 0 1, and then I have 0 1 0, then 0 1 1, then 1 0 0, we will have 1 0 1, then we have 1 1 0, the final one will be 1 1 1, that is the last one. Now, corresponding output, for example, if I have the output, that 1 bit will have 1 by 8th, then you have 2 by 8, that is 1 by 4, then we will have 3 by 8, then off, then we have 5 by 8, then 6 by 8, that is 3 by 4, then we have example with the 3 bit, then we have 7 by 8, then full scale. So, if I plot the curve, that ideal case, if this is full scale, that we will have full scale voltage would have come, then I for 7 by 8, actually if we take this is a full scale voltage, it is here that you will have for full scale, it is at this point it goes and meets. This actually will be meeting 7 by 8th point. It meets this is the ideal output. For example, if it is 0 0, you are supposed to get 0 volt, and per 0 1 1 it is supposed to be here. 1 by 4th would come per this, and then 3 by 8 would have been this. For off volt, this would have been here. V reference is taken as 1 volt. V reference is taken as 1 volt. Now, this is the ideal converter that you get when 1 1 1 1 is there, we supposed to get 7 by 8th of a voltage. If it is a 1 volt is full scale voltage, that at 1 1 1 we supposed to get 7 by 8th, and finally it reaches 1 volt. One LSP is left out to get the full scale voltage of 1 volt. Now, in actual case, if the gain error is there, instead of meeting it here, for example, 1 LSP gain error if it has, then this line will be meeting here. So, you will have the gain error coming into this. Now, this is a gain error. So, you have a gain error, you get a gain error which is not, because instead of meeting 1 1 1, instead of reaching at 1 1 1 it is supposed to meet here, but it had met at this point only. So, you have a gain error, because you got probably you will get a full scale voltage which is 1 volt at 1 1 1 1 itself instead of 7 by 8. So, if you look at this relation, then 7 by 8 volt at 1 1 1 is what supposed to get, but then if it is 1 LSP gain error, then you will have 7 by 8 volt at 1 1 0 itself reached. It is supposed to be ideal case. This is what we got it. So, this got a 1 LSP gain error at the at the output, that is at the maximum value you have 1 LSP gain error. So, this is one type of error. This is coming because the output voltage what we are getting is the multiplication factor is not correctly set. That is the reason to get the gain error. This is correctable actually, many of them give provision for correcting this, but many converters there is no provision to correct any of these errors. So, one have to aware of this the possible gain errors. Of course, one solution to correct this would be adjust the V reference, so that the gain error actually goes off. Now, the other error is similar way, if we can extend, for example, offset voltage error, we can have the same thing, for example, offset error. Take the offset error that we have similar seams that 0 0 0 if we take, and so on, we can have 8 bits. So, we will have the last one, for example, you have 1 1 0 and then the last one 1 1 1. So, you have 0 1 1 1 0 0 1 0 1. I will have I think 1 1 0, yeah, I think 1, this is correct, yeah. So, we will have here 1 1 1. So, we have corresponding to that, we will have the same output. So, 1 by 8, 1 by 4 and so on, we have finally 7 by 8 and then full scale. So, 1 by 4, then 3 by 8 off, then you have 5 by 8, then 3 by 4 and so on, we have this. So, if we have the we have 1 0 1 1, okay, here there is a missing point. So, I will change this, yeah, 1 0 1. This is correct, yeah. So, now we plot the regular expected output would be like this. So, we will have a full scale voltage. So, 7 by 8 actually supposed to meet here, and this supposed to meet 1 1 1 here. The case of offset voltage, it could be going like this. At 0 0 it is not actually 1 by 8. So, this is a offset error. Offset error is correctable. One can actually, if the provision is given, one can adjust the offset and make it 0, but offset drift is not correctable. There is no provision to adjust also. So, in many converters even offset voltage adjustment is not possible. This is offset voltage error. Then we also have linearity error. Now, what is done is the same converter, if I plot, you will have 0 0 as origin. I will put the, assume this is 1 1 1, then we have here 1 by 8, 1 by 4, then you have 3 by 4, then 3 by 8, then 1 off, 5 by 8, 3 by 4, then we have 7 by 8 and then full scale. Here we are supposed to go like this, and then is supposed to get this supposed to get 1 1 1 at this point. This is ideal, this is linearity error, this is ideal curve. In actual case, you may have like this, coming back, then going, coming back, even it can go minus and come back. This is actual. This is actually linearity error. Similarly, you will have a problem with differential linearity, that is adjacent ones are not going by 1 LSP, that is two outputs may not be showing exactly 1 LSP change, differential linearity. Differential linearity error. For example, if I have say 110, we supposed to get 110 supposed to give you 3/4 of a volt, and 111 supposed to give you 7/8 of a volt. The difference is 1 LSP, but the difference need not be 1 LSP. In ideal case, this can be for differential nonlinearity. The difference need not be the difference will not be equal to 1 LSP. This is actually coming as a differential linearity error. So, these errors are actually fixed, and these 4 errors, that is differential linearity error, linearity, and then offset voltage and the gain error, they are not a serious issue, but they can be corrected. In most of the converters it is possible, but the temperature related error is a serious issue. So, these 4 errors are correctable. Errors are correctable, but temperature related errors are not correctable. So, one have to worry about these. For example, if I have a to D converter which has 1 volt reference, and then 1 volt will be the analog expected output voltage. Now, let us see how these errors come into picture in a real converter. For example, we take a to D converter which has 1 volt reference, and then I have a V input here, and then you have a V output. So, we take 8-bit ADC. If we take a regular Zener, we have for example 30 ppm drift, 30 ppm per degree C drift Zener is used, then we will have a for 100 degree C, for delta T is equal to 100 degree C, the reference voltage drift would be the V reference drift would be 30 ppm into 10 power 6, the 30 ppm into 100 degree C. So, we put 100 degree drift, and then if it is 1 volt, then we take this 1 volt. So, that would be the actual drift, that will be 3000 divided by 10 power 6, that is equal to 3 millivolt. So, if it is a 8-bit converter, for 8-bit converter, for 8 converter 1 LSP would be 1 volt divided by 2 power 8, which will be nearly equal to 4 millivolt. So, this 1 LSP error is this V reference drift is coming less than 1 LSP. but for 16-bit converter, for 16-bit converter, then 1 LSB is equal to 1 into power 16, that comes to be about 16 microvolt. Then this 3 millivolt drift will be very huge. That means, if I want to go for 16-bit converter, then my reference also has to be stable, then only 1 LSB error is possible. So, for 16-bit converter, then for 16-bit converter, total error would be 3000 divided by 16 LSBs. That would be equal to nearly 200 LSB error. You see that soon the when you go for higher and higher bit converters, even the reference need to be very stable, otherwise there is no point in claiming 16-bit accuracy if you are using this 30 ppm reference voltage source. So, one had to go for 1 ppm reference source. For 1 ppm drift Zener, 1 ppm per degree C drift Zener, the total drift would be equal to, we will have 1 in 10 power 6 into 100 is the voltage drift. So, that would be equal to 10 power minus 4 volt, that is 100 microvolt, that is even equal to 6 LSB for 16-bit converter. Even 1 ppm reference you can get only 6 LSB 6 LSB. So, getting 1 LSB accuracy in 16-bit converter is actually very difficult. So, one has to aware of this problem due to the reference voltage drift. Similarly, offset voltage drift is another major error which actually affects the converter's accuracy very much. So, the second voltage is offset drift. Offset drift is given in terms of microvolt at the input. So, most of them give offset voltage is given in terms of set voltage drift at the input of ATD ADC is given in terms of 1 to 5 microvolt per degree C. So, if it is 5 microvolt, for example, for 5 microvolt per degree C drift case, for delta D is equal to 100 degree C, then total drift is 500 microvolt. Now, for 16-bit converter, this error equal to this drift would be equal to 500 by 16, that would be 32 LSBs. So, offset voltage drift also creates a problem, but then there is similarly gain drift. The gain drift also will produce an error that one can calculate from the data sheet what will be the actual drift. So, one had aware that in most of the 8-bit converters you can believe that resolution is 1 LSB and accuracy also easily achievable to the extent of 1 LSB. But for 12-bit and 16-bit one really have to calculate whether the accuracy and resolution are one and the same. So, the lesson is that for 8-bit converters, converters, 8-bit converters, resolution will be resolution and accuracy will be more or less same. That is, it is possible to get 8-bit accuracy against ambient temperature variation. However, it is not possible to get this in the case of 16-bit. So, in case of for 16-bit converters, it is difficult to get. 16-bit accuracy, 16-bit accuracy. So, one have to really compute and see in case of 12-bit and 16-bit converters what is the real accuracy. So, one should not assume that resolution and accuracy are same in all the A2D and DTA converters. So, these errors are there in DTA converter also. DTA converter also you will have linearity error, then you will have difference linearity error, you have offset voltage error, gain error, and then reference voltage drift error. So, these errors also can be computed in the same manner. Now, we can look at it, what are the other possible techniques we can use to reduce the A2D converter errors. One common technique that is used is ratiometric conversion. In ratiometric conversion, we can avoid the most of the temperature related errors can be reduced and going for ratiometric conversion. So, let us see what is the ratiometric conversion. Ratiometric A2D conversion. Actually, there is no separate A2D converters. How to use the ratiometric conversion? So, I will not call this a ratiometric ADC, call ratiometric conversion. This only how to utilize the converter. So, we have let us take for example, if we take a A2D converter, we have a ADC is there, then we have a reference voltage and then we have a V input. For example, I want to measure the resistance values accurately using for example, the bridge circuit, or I want to measure the resistance potentiometer value to be measured. So, I take for example, I can have a potentiometer like this, that is acting as input, then I give this as a V input. Now, I will get a digitized output here. This is a V reference. Now, we know that in A2D converter essentially the output digital value is nothing but the ratio between the two voltages, that is what is the input and output. So, digital output divided by full scale digital output is actually equal to V in by V reference. That means, if in actual case when VR changes with temperature, since this is already fixed, so we will get the digital output is changing, even V input is not changing. So, actually if VR changes, then for a given V in V in, digital output is changing. Suppose if in this case if I put V in itself, sorry, this is actually not V in, this is V excitation. If I make output is changing. Now V in depends on the excitation voltage. One solution for this drift would be make VR as excitation voltage. Then no drift due to VR. That is, what you do is we will convert with the excitation voltage and reference are kept same. So what you do is we will have the potentiometer here. For example, I want to measure a displacement, then what you do is the converter have a V reference here, V reference. This V reference is given to the ATD. Then you have the input here and then the output here. So V reference is equal to excitation voltage. So both are drifting. If the V reference drifts, then the reference to this also changing. The net result is it has no effect at the output digital. This is a digital word. So you have reference voltage drift has no effect on the output. So reference voltage drift will have no effect, effect on the output. Now of course the other errors will be still there, that offset voltage drift and gain error, all that will be there, but the reference drift, which is a major issue, particularly for 16-bit converters, it is a major issue. That error can be removed by going for the ratiometric conversion, but it is not possible all the time to go for ratiometric conversion. Wherever possible, one can go for a ratiometric conversion to avoid the error due to the reference voltage drift. Now we have processor based A to D converters, which are extensively used in the industry. So one had to worry about what are these errors involved, because most of them believe that if it is 8-bit converter, you will get 8-bit accuracy. That is no more true. So one have to verify when you are using a processor based system, inbuilt ADC is there. One have to clearly verify from the data sheet what is the actual error associated with the particular converter. Similarly, when you are using a DTA converter, one can also make a DTA converter using microcontroller, DAC using microcontroller. For example, in the case of microcontroller based system, we can also have a DAC, which we already discussed, that we have a plus voltage. For example, we can have a output which is a PWM, and then have a RC network which gives you the analog voltage, but then this is a very slow system. One can also make R2R DAC or binary weighted DAC using microcontroller very easily. So binary weighted DAC using microcontroller. So one can go for example, if you have a microcontroller I can have a binary weighted converter. For example, I can have a resistances connected to each one of them. For example, 4-bit converter if I want, then if all of them are 1, for example, this is MSB and this is LSB, then I will have the error, I will have the output voltage corresponding to the digital word. Of course, the resistors are to be scaled correctly. For example, if it is if this is 1 K, then the next one has to be 2 K, then 4 K, 8 K. Of course, this is one of the major problem that one has when you are dealing with the microcontroller, because having to get these resistors correctly is the major issue. Then immediately you can realize if it is a 16-bit converter, if you want to realize, then it is even much more difficult, because you do not get the correct values. Of course, one can have a 4-bit converter can be easily achieved using this binary weighted DTA converter techniques, because getting a separate A to D and DTA converter is expensive proposition, and if it is a simple system, it is easier to use microcontroller itself for A to D and DTA function to save the cost. So, we have discussed 3 A to D converters, that is a flash ADC, successive approximate ADC and dual slope ADC, and then we also shown how DTA converters are working both R to R network and binary weighted DTA converter, and how to use them with the microcontroller also we have discussed. So, we left with one more A to D converter, that is sigma delta A to D converter, that we discuss in the next lecture. Thank you.